Hi, y'all. I want to recap subatomic particles and atomic structure for you. By the end of this lesson, I want you to be able to explain and describe basic properties of an atom, super basic properties of an atom, and the subatomic particles within the atom. By reviewing information about subatomic particles and then also by being able to draw a model. If you have Play-Doh on hand, sometimes that kinesthetic action of actually building a model connects with your long-term memory process and helps you to really solidify all of these subatomic particles. Now, as these subatomic particles change, that's when chemistry really gets interesting. And so having the solid foundation on subatomic particles and being able to apply them to when the subatomic particles change, when the subatomic particles interact, is what we want to establish today. So we're looking for that really solid foundation. We're going to review some material. We're going to draw a model. Again, if you have some Play-Doh or some clay, building that model would really help as well. So let's just recap the really basic properties of our three subatomic particles. Our three subatomic particles are protons, neutrons, and electrons. These three things make up our atom. And you should know the charge, the mass, and the location of these three things. Those are our very basic properties about our subatomic particles. So the charge of a proton is a 1 plus, a neutron has no charge, it is neutral, and an electron is a 1 minus. Now notice, these aren't the actual charges. If they were the actual charges, they would have a unit on them, probably coulombs. And they would also not be a nicely rounded off single digit number, right? They do, protons and electrons do have actual charges, but we don't deal with these actual charges because the numbers are so bulky. So instead of dealing with the actual decimal charges, what we do is we deal with a relative charge. So a proton's charge is 1 plus relative to the electron. An electron's charge is 1 minus relative to the proton. The magnitude of their charges is the same. It's just that sign that is opposite. And so rather than dealing with the super bulky actual measured charges, we deal with this relative charge. It's like saying something like, if we have 35,000 people living in McMinnville, we could call that a 1 unit. And so if we find another city, let's say Forest Grove, that has a really similar population, we could say, okay, well, if the population of McMinnville is 1, then the population of Forest Grove is also 1. The population of Portland is probably 4 times that, and so we could call the population of Portland 4. Those would be relative populations. And it's convenient for us because we're avoiding using the super bulky decimal numbers, and we deal with the simplified relative numbers instead. That's what we're doing with the charge. Now, I say this so that you don't get further into chemistry and go start researching your, doctorate thesis on charges and be like, oh, Martin's lied to me. Okay, I'm not lying to you. We're just using relative charges. Similarly, we do the same thing with mass. Okay, so mass, we're also going to deal with relative charges in mass as well. Protons, neutrons, and electrons have actual masses measured in grams or kilograms. They're super awful decimals, as you saw in our scientific notation lesson. And so rather than dealing with these, we use relative masses. So if the mass of a proton is 1, a neutron has the same mass. It's also 1. Now, we do put a unit on this. We put the units of AMU. AMU means atomic mass unit. Okay, so atomic mass unit is kind of a scaled down version, much like if you're counting eggs, you would count in dozens instead of counting individual eggs you count in a unit, right? So we're going to count mass in a unit, and the unit of 1 is the mass of the proton, and a neutron has a similar unit. Okay, so again, these are relative, not actual. And then an electron is another interesting mass. So the mass of an electron is actually 0. That was poorly said. The mass of an electron is 0, not because an electron is massless. It's not. An electron is matter. It has mass. It takes up space. An electron has a measurable mass, and that's actually the mass we dealt with in kilograms when we were talking about scientific notation. However, relative to the mass of a proton, an electron's mass is what we call negligible. Okay, and so this is what I mean by that. Let's say the mass of a proton is 1.0072 AMU. Okay, and let's say the mass of an electron is 0.005, 5 AMU. Okay, so here's the question. If I add the mass of an electron to a proton, does it make a difference? So let's look at that. If we're going to add these two together, I'm going to get 7, 12, 1, 0.1. Okay, so, and then I'm going to round this off to 3 significant figures. So I'm going to take the first 3, and I'm going to say it's 1.01 AMU is the mass of a proton and an electron together. Okay, now let's look at what happens if I don't add in the electron. What's the mass of a proton by itself, rounded to the same place? Okay, so I'm going to again round to the first 3 significant figures. I cut off that 7. That 7 rounds the 0 up, so 1.01 AMU. So check it out. Whether I add in the mass of an electron or not, the mass of a proton or the proton and an electron together is the same when you round to 3 significant figures or when you round to the 100th place. The mass of an electron doesn't make a difference. That's why we call it negligible. It doesn't make a difference until you extend out your decimal place to the thousandths or to 4 significant figures, and only then do you start to see an electron making a difference. And that's only with 1 proton. When you get up into the higher you go on the periodic table, the more protons you're talking about. Even when you get to the 4th level, you're talking about 35, 36 protons. The mass of an electron is going to make even less of a difference. And so we say the electron's mass is negligible. The electron's mass is 0 when compared to a neutron or a proton. The electron is not actually massless. The mass of an electron is just not significant. It just doesn't make a difference until you extend the mass out far enough, like thousandths or the 10,000th place. Okay. Let's look at location. So when you start talking about electrons, protons, and neutrons, one of the first things you talk about is where they're located. So both protons and neutrons are located in the nucleus, and the electron is located outside of the nucleus. In what we call an orbital. You may have called it the electron cloud before. And this is one of the steps we get to take in this class is we get to look at that electron a little bit more specifically and where it lives and what kind of an effect it has. So we'll get to do that coming up here. Okay, next question. If you remove one, what do you get? So let's say we start with a carbon atom and we remove one proton. What do you get? What if we remove one neutron? What do you get? What if we remove one electron? What do you get? Now would be a good time to pause the video and think about that. All right, so if you remove a proton from carbon, let's say we have carbon 6. Is this a good one? Let's use lithium. Okay, let's use lithium. So lithium has 3 protons. Lithium has 3 neutrons. And lithium has 3 electrons. Okay, so let's start with this. All right. So there is my model of lithium. Okay, so what happens to lithium if I remove a proton? What do I have now? And you do not have lithium anymore. You actually have helium or a version of helium. So you get a different atom. Let's give lithium back that proton. Okay, what happens if we take away a neutron of lithium? What do I have? Do I still have lithium? Yep, I do. I still have 3 protons, which means I still have lithium. Notice that protons are what determines the element you have. So if I take away a neutron, I still have lithium, but the lithium weighs less. It's a lithium that weighs 5 now, instead of my original lithium that weighed 6. So it's still lithium, but it has a different mass. We call this an isotope. Isotope. Iso means the same. So it's the same element, different mass. It's called an isotope. All right, let's give that neutron back to lithium. And now let's take away an electron. So now what do I have? Well, I still have 3 protons, so I still have neutron. I still have 3 protons, so I still have lithium. That lithium still weighs 6, so I don't have a different isotope than I had initially, but I took away an electron. An electron doesn't change the mass, it does change the charge. So I used to have balanced charges, right? I used to have a 3 plus in the nucleus and a 3 minus in the electrons, and my lithium was neutral. Well, now I have a 2 minus in electrons and a 3 plus in the nucleus, and my lithium's no longer neutrally charged. It now has an overall charge of 1 plus. So 3 plus a 2 minus is going to equal a 1 plus. So my lithium is now charged. We put charges on the symbol in the top right corner. And so what we call this is an ion. If you have the same element with a different charge, it's an ion. Ions can be positive if you have more protons than neutrons. Ions can be positive if you have more protons than electrons. Ions can be negative if you have more electrons than protons. You can have positive and negative ions. But if you have a different charge, it's called an ion. Okay, so let's practice building a model here. Let's look at the carbon that we were initially talking about on the periodic table. Actually, I take it back again. Let's do fluorine. Okay, so take a minute now and draw a molecule of fluorine, just like I've drawn lithium above. You can make circles with pluses for protons. You can make circles for with N's in them for neutrons, and little circles with E's in them for electrons. So don't worry about where the electrons go at this point in time. You can just kind of put electrons around the nucleus. Now would be a good time to pause the video and try this. All right, fluorine should have 9 protons in the nucleus. It should have 10 neutrons in the nucleus. And then it should have 9 electrons out here in the cloud. Now, where do these numbers come from, you say? Well, let's talk about that. That's a really great question. Okay, so in order to figure out how many protons, neutrons, and electrons you have, you must be able to use the periodic table. So I have a copy of the periodic table down below. Some of the numbers are a little fuzzy, so you might want to have a copy of the periodic table next to you. And then I have hydrogen blown up here as my example. So let's talk about how you can use the periodic table to figure out how many protons, neutrons, and electrons you have. So there's 2 numbers on every element inside the periodic table. Now, depending on which periodic table you look at, those numbers are actually going to change locations. In this example that I have on the screen, you can see that there is a number here that is a whole number, and then there's a number here at the bottom that's a decimal. And it's actually really similar on this periodic table that I have copied here. The decimal is at the top, the whole number is at the top, the decimal is at the bottom, but that's not always the case. Depending on what periodic table you're looking at, they tend to flip numbers. If you got this periodic table in your packet, then actually both numbers are at the top. You see you have a whole number here and then a decimal right next to it. So depending on what periodic table you look at, those numbers can migrate. So you have to know that the whole number is always called the atomic number. Whatever the whole number is, it's called the atomic number. And the atomic number is the number of protons. So the number of protons equals whatever the atomic number is. Always and forever, no takebacks, no exceptions. The atomic number is the number of protons. And again, this is what determines the element that you have. So as long as you can look at a periodic table and you can identify the whole number, that's going to be the number of protons. You'll also notice that the atomic numbers form a pattern on the periodic table. If you are reading left to right, top to bottom, and you look at those whole numbers, you look at the atomic numbers, it goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, etc. Okay, the atomic numbers are sequential. Again, always and forever, no takebacks, no exceptions. That's not something we get to say in chemistry a lot. Almost always there's going to be an exception to a model or to a rule. But with the atomic number and the organization of the periodic table, there's no exceptions. Number of protons are sequential. They always get bigger, left to right, top to bottom. And this is called the atomic number. Now, the other number, the number that's a decimal down here, that's called the atomic mass or the atomic weight. And the atomic weight is made up of anything that has weight or has mass in an atom. Okay, now notice it's a decimal. And it's a decimal because it's an average mass of all the isotopes. So like we said, you can change the number of neutrons in an atom and it'll change how much the atom weighs or change what the mass of the atom is without actually changing the atom itself. So all atoms come with a variety of isotopes. You can have a carbon that weighs 12. You can have a carbon that weighs 14. Those are two of the isotopes of carbon. So which of those masses do we put on the periodic table? Well, we put an average. Now it's not a straight average like you're used to dealing with in arithmetic. We'll talk about how to calculate that average a little later on. But for now, what you have to know is that decimal is an average of all the isotope masses. So when you're looking at that number, we can figure out how many subatomic particles exist by looking at that number. But in order to do that, you have to round the number off. So you round the atomic mass just to the closest number. So for hydrogen, we would round it to 1. For helium, that's 4.0026. We'd round it to 4. For fluorine, that's 18.998. We'd round it to 19. So when you're looking at that atomic mass, just round it to the nearest whole number. Now, once you have rounded it to the nearest whole number, it now represents any subatomic particle that has mass. And if you think back to the last chart, the two subatomic particles that have significant mass are the protons and the neutrons. So that atomic mass that's given is protons and neutrons together. So in order to get the number of neutrons, you have to take that atomic mass and subtract off the number of protons. Okay, so for example, let's look at carbon, right? Carbon's atomic mass is a 12, and carbon has 6 protons. And so it's also going to have 6 neutrons. Fluorine that we looked at on the other page has an atomic mass rounded to the nearest whole number of 19. Fluorine has an atomic number of 9. So when you subtract that off, it has 10 neutrons. Okay, so in order to find out how many neutrons you have, you actually have to do a little subtraction to get that. And we'll do some of that practice in class. Now, atomic masses are fairly sequential on the periodic table also, but there are some exceptions where you move over to a new element and the atomic mass actually goes down. Not very many, but there are a couple. Now would be a good time to pause the video and see if you can find an exception in the atomic mass pattern on the periodic table. Okay, and one of the exceptions you may have found are elements 52 and 53. This is tellurium and iodine. And tellurium actually weighs 127.60. That is the atomic weight of tellurium. If you look at iodine's weight, it actually doesn't increase. It decreases. So its average mass is 126.90. So the atomic weight on the periodic table does have kind of a pattern, but there are definitely exceptions. So the periodic table was not organized off of atomic weight, at least not our current one. All right, now the question of the day, how do you find electrons? And that is a tricky question because it depends. It depends on whether you have a neutral atom or not. If your atom is neutral in charge, remember the charge is going to show up on the top right of your symbol. So none of the elements on the periodic table are listed as ions. None of them are listed as charges because there's no symbol in that top right corner next to the symbol of the element. So if you have a neutral element, like all the elements listed on the periodic table, that means your positives are going to equal your negatives, which means your protons are going to equal your electrons. If you have 6 protons and you have a neutral element, you're going to have 6 electrons too. If you have 9 protons and you have a neutral fluorine, that means you're going to have 9 electrons too. Now, if you have an ion, that's going to change because the protons are not going to be equal to the electrons. And when we get to ions, we'll talk about how to figure out the number of electrons at that point in time. So for now, you just need to know this part. For a neutral element, the number of protons is also the number of electrons. Now, is there a pattern on the periodic table for electrons? Yes. We actually spend an entire unit looking at the patterns of electrons on the periodic table because these patterns are what drives bonding. And so we will talk about these patterns coming up real soon. But until then, let's just say yes, there are definitely patterns. They are wonderful and magnificent patterns. We love them. They help us out. They make chemistry what it is. And we will look at those coming up. So I guess you just have to deal with a little bit of suspense until then. Okay, so that is our review of subatomic particles. Let me know if you have any questions. We will practice this in class. And so I will see you there.